Team Edhitha from Ramaiah Institute of Technology, Bangalore, India. And this is our flight attendance review. Let me introduce the 2023 competition team. Nihal, Team Captain and GCS Operator, 28 months of experience. Pratham, Systems Engineering in charge, 16 months of experience. Maurya, Safety Pilot and Technical Project Manager, 16 months of experience. Yashas, Structures and Propulsions Lead, 16 months of experience. Pranjal, Imagery and Cyber Systems Lead, 16 months of experience. Abhinav, Avionics and Navigations Lead, 16 months of experience. Satvik, Automations in charge, 16 months of experience. Yashaswini, Payload Operations in charge, 16 months of experience. Abhinava, Manual UI Operator, 16 months of experience. And this is 2023 Edhitha's Flightline. Our unmanned aerial systems features a robust quadcopter UAV equipped with a powerful autopilot subsystem and an innovative payload delivery subsystem that seamlessly integrates with ODLC imagery. This comprehensive system is fully capable of accomplishing all competition requirements and tasks with precision and efficiency, and hence perform fully autonomous search and rescue missions. The team timeline. A formulated and comprehensive flight plan must be executed meticulously during simulated full mission flights. The system must be modularized and designed to a plug-and-play standard. The team efficiently manages the entire system by utilizing GCS software to upload the waypoint course and search grid into the autopilot via a 915 MHz telemetry link. Once preparations are complete, the mission can be initiated with a simple command to arm and begin. Throughout the mission, the UAV autonomously navigates the designated waypoint course, and when it reaches the search grid, the manual UI operator can access the camera images in real time. These images are promptly analyzed, and any targets identified are designated for the payload delivery. Once a target has been identified, the airdrop system is triggered to release the payload, which is safely and accurately delivered to the target location with minimal delay. This process is repeated for each of the 5 designated targets, after which the UAV returns to its point of origin and lands safely. This year, for imaging, an ArduCam HQ camera featuring a Sony IMX477 sensor is being used, along with a 12mm lens. The combination of these features provides the system with images with target pixel dimensions of 81x58 pixel, which provides a sufficient clarity to classify each target. Enable effective object detection, localization, and classification. A manual UI system is developed incorporating the Jetson Nano as the onboard computer and a Ubiquiti Bullet M5 and PowerBeam M5 for reliable data transmission from the drone to the ground control station. The buttons have key bindings to improve usability. When the operator selects an object, they can stop and reposition the drone based on the object's calculated location using pixel coordinates of the target in the image. Accounting for various lighting conditions and the backgrounds, ideal values for speed of drone, FPS, exposure, ISO, and shutter speed were chosen. The payload, consisting of a water bottle, has been wrapped in a layer of foam to minimize any potential damage. Additionally, the bottle can be easily removed by the judges without the need for any tools. The mechanism operates on a straightforward yet effective stop and release principle. By repeatedly stopping and releasing a free-falling bottle, the mechanism ensures that the bottle maintains a controlled descent and never gains excessive speed before landing. The implementation for the mechanism is done with a pulley which can freely rotate using ball bearings. The payload housing consists of a plate with two 15-degree tapered extruded cuts that meet at a 60-degree angle. A thick guide for the locking rod is placed on one side of these extrusions. A C++ program is loaded onto an Arduino Nano microcontroller to facilitate the lock-unlock mechanism upon receiving the trigger to drop. Each lock and unlock action is received from a mathematical function that controls the payload's descent speed. The program enables the payload to drop faster at higher altitudes and gradually slows it down as it approaches the ground without requiring manual intervention. The optimal drop time is calculated based on the definition of the mathematical function, which uses delays with millisecond accuracy to choose when to stop and release. After careful consideration of factors such as flight time spent on waiting for drop and safety of the payload, the function has been expertly calibrated to achieve a total drop time of 12 seconds from an altitude of 100 feet. This level of precision ensures the payload is delivered safely and efficiently. 3 different types of communication systems have been implemented for the communication of the UAS with the GCS. The ground control station is connected to the autopilot via a 915 MHz RFT 900X which sends data using the Mavlink 2 protocol. This provides security encryption and low bandwidth transmission. Manual control uses a Radiomaster TX16 transmitter with an FRSky X8R receiver which connects to the autopilot through S-Bus. The transmission takes place at 2.4 GHz using the FRSky D16FR protocol. Manual control inputs are sent and the battery voltages are obtained on the transmitter screen for redundancy using the smart port of the receiver. Ubiquiti PowerBeam and Bullet are used for our communication link for high bandwidth data. These devices act as an Ethernet bridge transmitting data at 5 GHz. It handles imagery data for object detection, localization, and classification, commands to reposition the drone and triggers the drops. Finally, the manual UI operator is connected to the PICSOC via a serial connection. With the OBC acting as virtual router, there is a TCP connection outed to the operator's laptop. The team has designed and built the aircraft, which is tailored specifically for the SUAS competition. The quadcopter is an X configuration with dimensions of 32 x 32 x 20. The frame is constructed entirely of carbon fiber, ensuring optimal durability and strength. The design process involved careful attention to detail, utilizing simulation analysis to precisely route mounting codes. The frame comprises of 2 plates located at the top and the bottom of the structure, sandwiched by 4 folding mounts for the booms. The motors are attached to specially crafted CNC aluminium mounts situated at the ends of the boom. The propulsion system features top-of-the-line 100 kV motors and a 30-inch propeller system, which gives a maximum thrust of 31 pounds, providing excellent maneuverability and endurance. To ensure safe and efficient transport of heavy payloads, we have designed a unique landing gear system with non-interference in mind. Specifications of the aircraft are as shown below. Battery capacity 22 ampere, voltage 14S, propeller size 30 inch, ESC 80 amp, motor to motor distance 1170 mm, aircraft unit weight 37.2 pounds. The PICSOC Cube Orange Plus serves as the autopilot for the UAS, featuring advanced capabilities like redundant sensors and multiple communication interfaces for high performance, reliability, and flexibility in UAV applications. Ardocopter, an open-source software suite, is used to control the autopilot. Tuning is done by applying analytical techniques on flight performance graphs and auto-tuning the flight controller with respect to the frame. This enables easy compliance with competition requirements as the autopilot supports obstacle avoidance algorithms, auto takeoff and landing, and entire waypoint course implementation. As ground control station, the Mission Planner software is widely respected option that provides professional-grade functionality for mission planning and execution, including advanced flight mission planning, autonomous flight modes, and real-time telemetry and data logging for unmanned aerial vehicles. Dynamic obstacle avoidance is a crucial aspect of mission planning in order to ensure safe operations and avoid potential collisions with other aircrafts. This is accomplished through the use of unidirectional lidars, which are positioned towards the front and rear of the aircraft to detect obstacles in the flight plan. To achieve avoidance, the bendy ruler algorithm is utilized on the autopilot system, allowing for dynamic movement away from the detected obstacle while maintaining a safe distance. The bendy ruler algorithm actively scans the surrounding area in various directions in search of open spaces, with the ultimate goal of selecting a direction that is both open and leads towards the final destination. Under alternatives considered, the table reads as follows: the system, the alternative, and the rationale for discarding. Under aircraft, off-the-shelf frame or commercially available frame was discarded due to lack of design flexibility and higher manufacturing costs. As a power source, lithium-ion battery packs were discarded due to low discharge current rates leading to high voltage sags. Under airdrop, winch mechanism using brushed low RPM motors was discarded due to its inability to drop within a reasonable amount of time due to mechanically limited maximum speeds. Another airdrop alternative was by using back EMF of brushless DC motor to slow itself down. That was implemented by shorting the cables of the motor with each other. This alternative was also dropped due to inability to make reliable calculations. Under autopilot, here 3 GPS was discarded due to insufficient monetary funds and RTK precision not required. Under obstacle avoidance, Dijkstra's algorithm was avoided due to its inability to avoid dynamic obstacles. Under communications, due to insufficient monetary funds, use of Ubiquiti Rocket M5 AC Light instead of Bullet M5. Light Beam M5 instead of Power Beam M5 was discarded as an alternative since it has a SISO antenna which is unreliable for UAV applications. Under imaging and ODLC, ArduCam 64 imaging sensor was discarded due to insufficient GSD with a standard focal length and no option to attach external lens. Deep learning based classification was discarded after unsatisfactory accuracy due to insufficient training data. The team faced multiple risks during developmental phase and during mission testing phase. These risks and their proactive measures and mitigation response taken by the team are mentioned below. Guidelines were referred to before handling any sort of power tools to avoid tool-related physical injuries. Filtered masks, glasses, and gloves were used during fabrication of carbon fiber to avoid airborne carbon fiber dust. Adequate training is given to members who are dealing and using batteries to avoid improper battery handling. making sure the voltage and current rated for the component is met and cross-checking power source ratings using a fluke meter to avoid burning of onboard electronics. Beeper is activated during an active payload release so that the bystanders can stay clear, and flights are tested in an empty field or empty surrounding of about 3 miles to avoid bystander accidents. Required calculations and simulations are done before adding any new component to the SUAS frame. Fabrication errors are redeemed during the prototype phase. Financial and time restriction risk was circumvented by better management and planning during developmental phase. Lock nuts and Loctite has been used to ensure fasteners are in place to avoid debris falling off the UAS. During vision testing phase, instruments such as anemometer were used to calculate unanticipated wind speeds to avoid unanticipated weather conditions. To avoid communication losses, extensive range tests were done before integrating with the UAS. Failsafes have been set such that if any of the systems are down, the failsafe is invoked and the drone returns to launch. To avoid autopilot failure, industry standard flight controller is chosen along with extremely reliable autopilot firmware. The servo is placed in a default lock position to avoid release mechanism failure. To avoid the risk of GCS being unoperational, UPS is carried to the flight line as a power backup source. A series of tests were conducted to ascertain the reliability of the imagery hardware. Over the past several months, approximately 4,000 images were captured to assess the camera's performance under varying lighting conditions and from different altitudes corresponding to those during the mission. Approximately 2,000 of these images were captured with the hardware mounted on the UAV. The various measures were taken to ensure optimal image quality to prevent undesirable effects such as jello effect and image blur. A vibration dampener mechanism was developed through several rounds of rigorous testing. The average resolution of an object in the images was found to be approximately 80 x 60 pixels, which closely approximates the airdrop subsystem underwent rigorous testing to identify potential points of failure, including sudden stops causing jerks and rope winding issues. Several issues that emerged during the testing phase were effectively resolved through minor design modifications, such as the use of tapered supports, proper winding techniques, and the incorporation of ball bearings. Thanks to the fixed position hold capability and rapid descent speeds during the initial stage of the drop, external factors have a minimal impact on the drop accuracy. Moreover, the mathematical function controlling the drop has been meticulously fine-tuned based on actual drop characteristics observed during the testing phase. Following the optimization of the drop function, a total of 38 drops were conducted, of which 36 were deemed successful. The 90th percentile drop accuracy was recorded at a distance of 4 feet from the target. Confidence with airdrop 10 by 10, highly confident. The tests performed in the communication systems include logging of throughput and packet loss statistics for different distances from home location, and range is calculated as a distance until which the first packet losses occur, which are reported as failsafe. This logging was done on a regular basis during other objectives, and hence it led to gathering a huge variety of data to draw accurate conclusions from. The manual control radio link performed well up to a distance of 2 miles from home location. The throughput and packet losses are as shown. The safety of all systems and personnel was of paramount importance during the rigorous testing of the aircraft. The practical rigidity of the aircraft was found to be ideal, with a wing loading that ensures heavy payloads do not adversely impact the frame. The propulsion systems underwent a bench test of 6 hours at full throttle and were determined to be reliable. To evaluate the performance of the aircraft, initial flights were conducted in stabilized mode, with further tuning carried out to optimize the harmonious interaction between the autopilot and the aircraft. The batteries were subjected to multiple full-cycle discharges to assess their practical endurance, which was found to be 29 minutes at full loaded weight. Numerous high-speed tests were performed to arrive at the conclusion, as evidence by the proof of safe flight section, that our aircraft can fly at speeds of up to 22.5 meters per second for up to 12 miles, even in windy conditions during a single flight. Our aircraft boasts an impressive total of 120 documented flights, with approximately 40 hours of total in-flight time. The autopilot system is a critical component of our onboard systems, and its performance was expected to be nothing short of exceptional during our tests. To ensure that it met our high standards, we implemented a multi-stage and conducted thorough calibrations. Following this, the autopilot was subjected to numerous different types of auto missions in a variety of environments, including high wind conditions. After each flight, a detailed log analysis was conducted to assess the desired movement versus observed movement, with special attention paid to factors such as vibrations, EKF variances, and other event failsafes. Number of auto flights conducted, 207. Time spent in manual mode, 4867 seconds. Waypoints attempted, 5807. Waypoints hit 5758. Average waypoint miss error 99.173%. 99.173% accuracy or 0.827% miss error. During the test performed using Vision Planner, it was possible to view the proximity of the obstacle as well as the distance at which it was detected and avoided. In addition, while conducting the experiments with LiDARs, the following information was gathered. During the test performed using Vision Planner, it was possible to view the proximity of the obstacle as well as the distance at which it was detected and avoided. During the experiment, the distance between the obstacle and the drone was systematically increased by 1.64 feet increments. Despite this increase in distance, the drone was able to avoid the obstacle successfully, but only up to 8.20 feet object distance. Upon completion of the testing, the collected data indicated that LiDAR detected the obstacle consistently every time. Furthermore, the obstacle was successfully avoided in 9 out of 10 attempts, as per our findings. Drawing from our experience at Edhitha, we acknowledge the potential implications of Murphy's Law. To counter this, we prioritize rigorous training of our competition team with our competition systems through full mission testing. Our mission tests involve exact replica of the evaluation procedure implemented by the competition judges to the best of our abilities. During these tests, our competition team practiced setting up the systems within the allocated setup time, allowing additional time for mission briefings. Once the mission was initiated, it was ensured that only 3 designated operators, as designated in the competition, were responsible for its execution. In total, we conducted 4 full mission flights, all of which were successful. The following are the results. We hence expect our performance in the competition to be similar to our tests, and hence we have a high confidence in obtaining a score above.
In summary, Team Edhitha from Ramaiah Institute of Technology has utilized a systems engineering approach to design our unmanned aerial systems aimed at addressing the problem statement of the competition with high confidence. Our system comprises a proprietary quadcopter design featuring a 30-inch propulsion system with significant emphasis placed on enhancing the autopilot system to achieve maximum autonomy. The payload release mechanism underwent extensive iterations and redesigned to ensure optimal functionality. Additionally, system integration was a top priority, ensuring seamless performance during the competition. Our team has devoted significant effort to this project over the past year, motivated by our desire to expand our knowledge and skills beyond the confines of our academic curriculum.